Good morning and welcome back. So, where we are is we're in the middle of talking about the forces of evolution. And as I mentioned earlier, we're in the mindset of adopting the triumvirate of abstraction, idealization, and simplification. What that means precisely is that we're thinking of the genome as a collection of independent genes. For the moment, we're imagining that each gene has only two flavors, and we're asking questions about what changes the frequencies of those two alleles over time. And that's what we mean by the evolutionary process. So, here, what we're going to do is we're going to talk about natural selection. And this is probably the most familiar ingredient of evolution that's well known to almost everybody with sort of a reasonable scientific uh, level of knowledge, I would say. And I talked about drift first because I thought it was important to offer it as the appropriate null hypothesis, really, as opposed to selection. Like, not everything that we look at in the world around us necessarily should be viewed through the prism of selection. So the concept here is that we have these different alleles, and the word we're going to invoke is that they have different fitnesses. And I'm going to mathematicize that idea using ideas from population genetics in a little bit. But before doing so, let's just once again sort of remember Alfred Russel Wallace and Darwin. Darwin's comment: this preservation of favorable variations and the rejection of injurious variations, I call natural selection. So, as you see in the top, the variation, members of the population vary in the traits they display. Offspring, inheritance. Offspring tend to resemble their parents. So, we made a lot of noise about that earlier in the term. And then this is the key operative word: differential reproductive success. Brighter beetles are bitter, and predators learn to avoid them. Bright beetles are more likely to survive, and thus more likely to reproduce than are duller colored beetles. And so, over time, as you see on the bottom, evolution by natural selection, the proportions of the different variants in the beetle population change over time. Good. So we've already talked about beak size and diet category, about the Galapagos, about the finches, and their propensities to utilize different seeds as a function of their beak size. I just, as an aside, want to remind you that it's cool that one can measure the force it takes to break open a seed. I've already remarked on the fact that I find it subtle and not at all obvious that, a half a millimeter or a millimeter change in the beak depth is sufficient to lead to a substantial difference in the ability to break open a seed. And, these are different species. You can see by looking at them that the nature of their beaks are different. And thereby, which seeds they tend to eat will be different. When we're in the Galapagos, we'll definitely see opuntia, and I'll be sure to point that out. So we've already talked about the fact that there have been droughts on Daphne major, that leads to this what I would say is a selection process whereby the large beaked birds actually are favored. And so that's the kind of thing that we want to now address using the ideas of population genetics. So let me set up the picture, which is we're going to here, probably on the homework I'll think about the haploid case, but here we will think about the diploid case, where we have some organism, and I'm in this mindset of one locus, two alleles. So here I'm going to label, this is in the context of sickle cell for hemoglobin. I'm going to label the sickle cell allele as S and the normal allele as A. And what you see on the two histograms on the right is really, really interesting. So what we're going to do is we're going to introduce a notion of fitness where for each one of these different genotypes, we're going to say that it has an associated fitness. Like WSS is going to be the fitness for the SS allele. AS is going to be the fitness for the AS heterozygote, and AA will be the fitness for the AA homozygote. Now, what's interesting in the first of these histograms is that you see that the heterozygote is favored by the most. But the homozygote SS is very unfavored in all populations. So what that means is that, to me, is we should expect some sort of an equilibrium where there's a low frequency of S in the population such that AS has a reasonable chance of occurring, but SS is really not favored. So that's the kind of picture. And what we're going to do is we're going to work out the population genetics. We're going to work out the flow over time. In other words, these graphs, note what's plotted. The graph, the y-axis is P, the probability of finding A1, the A1 allele. So what you see is that if A1 starts out very high, which would favor the A1 homozygote, then over time the probability of P will go down. If, on the other hand, if little p starts out 0, meaning there's no A1s in the population, that too, or a very small number, that too will tend to increase because the winner here is the A1A2 heterozygote. So this is the case that I really want to illustrate. I'm going to show you a Python code at the end that I have that will allow us to sort of explore these things. The time dependence is also very interesting, and I'll give you the opportunity to explore this in the homework. So what I want to do now is I want to try and do a few calculations, and then once I've done those calculations, then the plan is to the plan will be to go to my code so we can take a look. Okay, so here we are. We're talking about selection, so population genetics of selection. And let me introduce some notation here. Okay. So here's the idea. I want to start out with this simple toy model that I've drawn here already. So what is this saying? It's saying that for the purposes of argument, I'm going to assign a fitness of 1. The relative fitness is really all that matters for the moment. I'm going to assign a fitness of 1 to the A1 homozygote, a fitness of 1 to the A1A2 heterozygote, and punish the A2 homozygote with this selection coefficient, a little s. So notice that the fitness of the A2 genotype is lower than that of the other two. And now what we can do, the way I want you to think of what's going to happen in going from generation n to generation n plus 1 is that we're going to draw from our urn the way we've done in the past, but we're going to alter the probabilities by multiplying them by the fitness. So let's just see what I mean by that. So the probability that I reach into my urn and grab A1, that I get the A1 genotype, is p squared, right? Because p is the probability of drawing an A1. The probability of getting an A1A2 is 2pq, and the reason for that is that the first draw I could get a p, an A1, and the second draw I could get a A2. That has probability of pq. Or the first draw could give me an A2, that has probability q, and then the second draw could give me an A1, and that gives me that has a probability p, and so the total probability is 2pq. Finally, the probability of drawing A2 is q squared. But now I'm going to punish it with its fitness, which you see right here. Now, what the problem with that is that if I follow that through, then the probabilities will decrease over time. In other words, the sum of these three things is not 1. So what I need to do is I now need to normalize. And the way that I normalize is by dividing by the sum of these three fitness-weighted probabilities. You see that I can define what I'm going to refer to as the average fitness, W bar, as p squared plus 2pq plus q squared 1 minus s, because p, so let me expand this out. Notice that I can rewrite this as p squared plus 2pq plus q squared minus q squared s. But this whole thing is p plus q squared, which is equal to 1. So that's why this thing ends up being equal to 1 minus q squared s. So for this little toy model, the idea is that I'm going to do my breeding experiment by drawing from the urn, but there's going to be a modification because, in a way, you can think of it as that I punish the q squared when I draw it out. Okay, so let's actually look at the change in allele frequencies. So you'll recall that we wrote down what I'm going to refer to as a kinematic formula. The kinematic formula was, it allowed us, given the observed genotypes, to figure out the probabilities of the alleles. And so here what I've done is I've written out p prime, which is the probability of the A1 allele in the n plus 1th generation. How do I find that? Well, the probability of pulling out two A1s is p squared over w bar. Okay, maybe I should have given another column here. I could have said probability. And then this one would be p squared over w bar. This one would be 2pq over w bar. And this one would be q squared 1 minus s over w bar. Now these things are normalized, right? Those are the probabilities of getting A1A1, A1A2, and A2A2. So, at any rate, now in light of that, down here what you see is that p prime, the probability of the next generation, is p squared over w bar. That's the probability of having the A1A1. And then here I have 2pq over w bar. That's the probability that I will have the A1A2 genotype. Then I factor out this p, as you see here, and I'm left with p prime is p over 1 minus q squared s, and that allows me to compute, as you see down here, the change in allele frequency. The thing I want to know is I would like to have a dynamics. I would like to know from one generation to the next, how does p get updated? How does the allele frequency change from one generation to the next? Let's look at that a little bit more generally, and that's what I show you here. So here the concept is the same, and maybe I will once again write my probabilities. So probability. This guy is p squared w11 over w bar. This is 2pq w12 over w bar. And this guy is q squared w22 over w bar. Where you see I here define the mean fitness. Now, let me pause for a second and ask you to do a thought experiment in your own mind. If you were to make a plot of w bar, what do you think that plot would do over time? Again, what is w bar? W bar is the mean fitness. So I expect that over time the fitness is going to increase in the population. So now I can compute the change in allele frequencies under selection. So this is the general case, right? So I've made no specifications here about which one is larger. I've said the fitness of the A1A1 genotype is W11, the fitness of the A1A2 genotype is W12, and finally W22 is the fitness for A2A2. So how do I compute the probability of the A1 allele in the next generation? Well, I use the usual kinematic rule. The kinematic rule says you take the probability of the homozygote, that's the p squared guy, and you add to that 1/2 of the probability for the heterozygote. Remembering that the heterozygote only brings 1/2 as many copies of the A1 allele as the homozygote. So this tells me that delta P, the change from one generation to the next, is given by this simple formula. So it's a very nice formula, which tells me delta P here is given by P divided by the mean fitness, and then times this quantity, which you can think of as basically a driving force. So now, to finish up this whole story, what I want to do is I want to show you this little Python code. So let's just, the top part doesn't even matter. So here's the formula that I just wrote down. You see up here. Okay. So W bar is the mean fitness, as we described previously. And now what's done here is we define the fitnesses. So WAA we take to be 1. W little a we take to be 1. And then W big A little a, which is the heterozygote, we take it to be favored with selection coefficient S. Then what happens here is we compute W bar. You can see that on this line. That's exactly the formula I just showed you. And then we compute delta P. And that thing is according to the formula up at the top, right here. So that formula is what is represented right here. So we compute this. So I hit return. And now all I'm going to do is I'm going to plot that. So there's the plot. Now what does this mean? It's telling us how the delta P in any generation. So what do I notice about that? I notice that if I happen to be at P equals 1/2, then there's no delta P, meaning that's a fixed point. One thing I'm curious about is where is S set? I'm not clear on where I did that. Okay, well anyway, so now let me show you something else. Let's say that I say that the homozygote a little a is down in fitness. Before I run this, what's your expectation? If the little a is unfavorable compared to either the big A little a or the big A, what's going to happen in this population? So what's going to happen is that the little a homozygote is going to disappear. So let's see how that shows up in the delta P. So notice that delta P is always positive. What do I mean by that? I mean that no matter where we are in P space along the x-axis, remember P can only be between 0 and 1, the delta P is always positive, meaning it's always pushing it towards P equals 1. And in the long time limit, after many generations, then little p will be 1, which means that all the alleles will be A1, or big A in this language. So, I think, that's the essence of what I want to show. So let me go back to the previous case because I find that to be more interesting somehow. Let's actually choose the selection coefficient to be bigger. So I'm going to change it just for kicks. So we rerun this, and then we make a plot. Yeah. So let me also take this guy down. So little a is less favored. So you can see how this plays out. And in this case, what have I done? I see. So let me just choose a number here. So big A little a is 1.2. Now I basically have favored the big A, and you can see what happens is we shift the equilibrium point. So what's the sort of thing that you're going to have a chance to do in the homework is to integrate the equations over time, in other words, over generations, to figure out what happens from one generation to the next. So this was my little story about selection. It was a very superficial introduction, but I think it gave you the essences of things.